Palu, Indonesia, 3:27 a.m. The ground cracked open beneath 400,000 people. Magnitude 6.7. Depth 10 kilometers. Shallow enough to feel everything. Buildings came down. Hospitals pushed patients into the streets. Families ran with nothing but the clothes they were wearing. But here is what makes this different from any other earthquake. This exact city. This exact fault. 8 years ago, it already did this. And that time, it killed thousands and swallowed entire neighborhoods into the earth. Tuesday morning, it moved again. This is not just a breaking news story. This is a system that has not finished. The sequence of events on the morning of June 16, 2026 unfolded with the specific brutal logic that only earthquakes produce. At 3:27 a.m. UTC, the initial rupture occurred. The epicenter was located approximately 43 kilometers east-southeast of Palu, the provincial capital of central Sulawesi. Depth 10 kilometers. That number matters more than almost any other figure in this story, and we will return to it. Within seconds, seismic waves reached the city. Residents across Palu described the same experience, a deep, violent rumbling that built rapidly in intensity. One local resident told reporters it was the strongest shaking they had felt in years. That description is not hyperbole. A sustained 6.7 at shallow depth, directly beneath a populated urban area, produces ground motion that is fundamentally different from a deeper quake of identical magnitude. People did not wait for instructions, they ran. Out of apartment buildings, out of homes, away from anything that had walls and a ceiling. Streets and open parks filled within minutes as the city's instinct, hardwired by history, kicked in before any official guidance could be issued. Hospitals began evacuating patients outdoors, including critically ill individuals still connected to IV equipment. Hotel guests and staff evacuated their buildings. Images circulating in the hours that followed showed partially collapsed roofs, shattered walls, and debris fields spread across multiple streets throughout the city. The main quake was followed by a sequence of aftershocks, the strongest registered at magnitude 5.2. Two additional aftershocks measured 5.0 and 4.9 respectively. Indonesia's Meteorological and Geophysical Agency monitored the sequence and confirmed no tsunami warning would be issued. That confirmation mattered enormously in Palu, but it did not stop thousands of residents from moving away from the coastline anyway. The memory of what this city survived in 2018 does not require an official alert to activate. Pull back from the streets of Palu and look at where this city sits on a map. Sulawesi is not a typical Indonesian island. It is one of the most geologically complex landmasses in Southeast Asia, shaped by the convergence of multiple tectonic plates pressing against each other from different directions simultaneously. Where most islands experience stress from one primary fault system, Sulawesi sits at an intersection, a meeting point of the Eurasian plate, the Australian plate, and several smaller microplates that grind and shift in competing directions. Palu itself occupies a narrow valley flanked by steep terrain, with a bay that opens to the sea. That geography is not incidental. The valley that holds the city was carved by the Palu-Koro Fault, one of the fastest-moving strike-slip faults on Earth, moving at an estimated rate of roughly 40 millimeters per year. For context, that is among the highest fault slip rates measured anywhere in the world. Zoom out further. Indonesia as a whole sits on the Pacific Ring of Fire, a 40,000-kilometer arc of tectonic boundaries and volcanic systems that encircles the Pacific Ocean and accounts for approximately 90% of the world's earthquakes. Indonesia alone experiences thousands of seismic events annually. The country is not simply earthquake-prone, it is earthquake-defined. Palu's population of roughly 400,000 people lives inside this system, not near inside it. The 10-kilometer depth reported for this earthquake is the detail that separates a damaging event from a potentially catastrophic one. And understanding why requires a brief look at how seismic energy actually behaves underground. When a fault ruptures, it releases energy in the form of seismic waves that radiate outward from the point of origin. Those waves do not travel at equal intensity in all directions. They attenuate, meaning they lose energy as they travel through the earth. The deeper the origin point, the more material those waves must pass through before reaching the surface, and the more energy is lost in that passage. A shallow earthquake at 10 kilometers depth gives seismic energy almost no distance to dissipate. The waves arrive at the surface with most of their original force intact. This is why a 6.7 at 10 kilometers can cause more structural damage than a 7.0 at 50 kilometers. Depth is not a secondary detail. It is one of the primary variables in determining what a quake actually does to the ground above it. The Palu-Koro Fault, the system responsible for this region's seismicity, is a strike-slip fault meaning the two sides of the fault move horizontally past each other rather than one plate overriding another. Strike-slip motion tends to produce very efficient energy release at the surface level, with strong lateral ground shaking that is particularly destructive to the sides of buildings and to infrastructure not designed to handle horizontal force. This is also why the 2018 disaster produced liquefaction at such devastating scale. Liquefaction occurs when water-saturated soil loses its structural integrity under sustained seismic shaking, essentially behaving like a liquid for a period of time. In Palu in 2018, entire residential neighborhoods were consumed as the ground beneath them turned fluid. The phenomenon requires a specific combination of soil type, water saturation, and shaking duration. Palu's geography, with its bay, its river delta sediments, and its history of land use, creates conditions where liquefaction risk is not theoretical, it is baseline. Tuesday's earthquake did not trigger confirmed liquefaction events, but the underlying conditions that enabled 2018 have not changed. The numbers that will eventually define this earthquake, the casualty count, the displaced population, the structural loss assessments, were still incomplete in the hours following the quake. As of the immediate aftermath, no confirmed fatalities had been officially announced, though damage assessments were actively underway, and the National Disaster Management Agency was still gathering information from affected areas. What was clear, without waiting for final figures, was the human reality on the ground. Families standing in open streets at 3:30 in the morning, hospital staff carrying patients on stretchers into outdoor spaces, setting up makeshift treatment areas away from buildings that could still be vulnerable to aftershocks. People waiting for information, watching their homes for signs of structural damage, trying to decide whether it was safe to go back inside. The instruction from authorities was direct. Do not return to damaged structures until formal inspections are completed. That instruction sounds simple. For a family with nowhere else to go, it is not simple at all. Emergency teams were mobilized and operating across the city. The scope of their work: checking buildings, roads, bridges, and utilities across a major urban area hit by a shallow 6.7 is significant. These assessments take time, and during that time, the aftershock sequence continues. The June 16th earthquake is a single event within a system that does not pause between events. The Palu Coro Fault has been accumulating stress for centuries. The 2018 magnitude 7.5 earthquake released a massive amount of that stored energy, but fault systems do not discharge completely in a single event. Stress redistributes along the fault and to adjacent fault segments. What researchers study in the years following a major rupture is where that redistributed stress has migrated, and which segments of the fault are now closer to their own rupture threshold. A magnitude 6.7 in the same region 8 years later raises a specific set of questions that seismologists and disaster management officials are now working to answer. Is this event part of the ongoing stress redistribution from 2018? Does it indicate increasing activity along a fault segment that had been relatively quiet? What does the aftershock sequence, its magnitude distribution, its geographic spread, its decay rate, reveal about the state of the fault system beneath Palu right now? These are not rhetorical questions. They are the operational questions that will shape emergency response decisions, reconstruction guidance, and long-term urban planning for a city that has already been rebuilt once from near total destruction. Palu exists on one of the most dangerous fault systems on Earth. The city has rebuilt. The city has absorbed another earthquake, and the fault beneath it is still moving, 40 millimeters per year, in every direction that matters. The ground is not done.